Okay, this is a bit of a summary of forces for Year 10 students. So what we could think about is an object, and we think about the forces which are actually acting on it. Now let's just imagine that it is stationary, it's not moving, okay? So this is a word you'll see quite a lot, just means not moving, okay? And it's very weird looking at my own handwriting stuff on the screen. Not moving, okay? They might also say at rest, okay? Both just mean not moving at a speed of 0 meters per second, okay? But there are still forces acting on it. We can't say there are none. What we've got, first of all, of course, is the actual weight of the object. And we can also just bring in that idea about what weight actually is. It's just its mass multiplied by the strength of gravity, which on Earth, hopefully you remember, is 10. Now, if that was the only force acting on it, then they'll be saying, well, right, so hold on, it's getting crushed into the Earth because there's nothing that's stopping it from accelerating downwards. So what we've also got is the normal contact force, which we can represent using this here. And you see these are both roughly the same size. I've tried to make them exactly the same size. So that's saying there's no acceleration, there's no resultant force, okay? Because what we could just say, if that's W, and the total resultant force is 0, well, that would just mean this is minus W, okay? That minus shows it's in the opposite direction, okay? And so what we get is the total force, the resultant force, which is called Fr, is equal to 0, because W plus negative W equals 0. Now, let's just put our little police thingy away. There's a bit of a disadvantage to these diagrams with using this object because it's a lot more visually complicated. It's more difficult to sort out the data we're actually working with. So often, I think I've gone through this before, is we will use as an example, we use to show that example, we will just use a little square, okay? So we might just have this to represent our little car thingy, okay? Now, this will relate to, and let's draw a bigger one. I don't like that. There, okay. This relates to one of our lessons, is the weight in the car. I'll write car up here, and I'll write the F for front, F for rear, R for rear. We look at the weight, and for the weight, we represent it going from this point here, okay? There's our weight, which is equal to mass times gravity, from its center of mass, okay? That's where the weight is acting from, or where we can imagine the weight acting from, okay? We can kind of imagine that your weight is probably acting from around about your belly button. A car's weight is probably acting from somewhere towards the front. Not exactly at the front, but towards the front, because the engine has got so much mass compared to the rest of it. And also we've got this normal contact force. Now, because it's a contact force, we would represent it actually where the force is happening, which is where it contacts the surface, okay? So we want that to be roughly the same length as the weight. So let me see. Yeah, that looks okay. This is just, you don't have to worry too much about this stuff, but it just helps us to think about the diagrams, and sometimes they'll represent them like this. For your level, they don't really. They'll probably represent the normal force from there, okay? Now, so there is our object. It's sitting there, and remember, it's at rest. It is stationary. Okay, 0 meters per second. Now, let's go and imagine what is going to happen whenever this yoke starts moving. Okay, so here it is again. We're not very worried about these forces here, because what you'll also see in exam questions is that it'll be on a flat, straight road. Okay, which means all we're worried about is changes of speed. Okay, this is what we're usually thinking about. So we don't need to worry about changes of direction, because the geometry within that's a bit more complicated. And that means it's quite difficult to work with this sitting here, because it wants to overbalance. The center of gravity in this is probably somewhere about here. It's close to the tops of the wheels, so it's easy to knock it over. So I'll put it like this. So right now it's at rest. It's not. Well, it should be at rest. It should be not moving. But let's say the police want to go and arrest somebody. Well, they're going to have to increase a force on it. Okay, so they're going to have to not increase. They're going to have to create a force on it, which comes from the engine. So we've got this here, and let's use our little box to represent our car. We're ignoring weights. Jeez, that's a horrible box. We're ignoring weight and upthrust because we can't see them in this perspective anyway, okay? Because, you know, those arrows we wouldn't really be able to see. But let's think about that thrust force. Okay, we start off and we give a bit of thrust at the beginning, okay? So let's say at the very beginning we've got this thrust force, okay? And we'll call the resultant force, I don't know, 10, okay? Let's say the mass of this object is 300 kilos. Well, this force is going to make this accelerate because we've got a resultant force. It's going to accelerate forwards. So the information we can get from this, well, we can know its weight, but we don't care about that. Remember, we're on a flat, straight road, so we're not very interested in the weight. But we can get this force and this mass, we can get the acceleration. Now remember, when you're answering exam type questions, it's very useful to take the data you've got. We've got a force, we've got a mass, okay, so the force is 10, the mass is 300, and from that, the question was probably asking you about an acceleration. We don't know that. Now that you've written out the bits of data, the two bits which you have, and the bit you're interested in, it's much easier to work out what equation you're looking for. Oh look, FMA, force equals mass times acceleration. And our force, well, we already know that is 10 is equal to 300 multiplied by A, which we don't know. Different ways of approaching this. I just like to sort of realize, all right, there's a missing value from here. So 300 times something is equal to 10. So it's got to be something very small to make this into a smaller quantity. And of course, the way you could do it is 10 over 300 gives us that acceleration, okay? So 10 divided by 300, remember, you can do 1 over 30. So, and that just becomes, use a calculator, but is 0.03 recurring, or 0.0333333, and so on, okay? Don't leave it as a fraction, okay? Leave it, actually evaluate it, put it into decimal. That's what they seem to like. Anyway, so far so good. To come back to it, we know the mass of this, we know the force, and therefore we can find the acceleration, okay? One really important thing to consider is that that acceleration is going to change. Now take a moment and think about why that is. Why is this acceleration not going to stay exactly the same? I've chosen my numbers pretty badly. That's a very small force and a very small acceleration. It's not very useful, okay? But well, let's just, excuse me, let's just go with it. Now, as soon as this starts moving, what is it going to meet? It's going to meet some air resistance, isn't it? So this is just for one moment. It's like a snapshot in time. Just one little moment in time, not a moment of force. Okay, let's go to the next moment. So, you know, a few seconds later, right? Again, we still have our little police car. It's still got a mass of 300 kilos. We're ignoring the fuel it's burning because that makes our calculations more complicated. Let's just say that the engine is still giving this pathetic weeny little force of 10 newtons. Well, now we've got some air resistance, don't we? Let's say the air resistance is, we'll go for simplicity's sake, we'll say 5. Smaller arrow, 5. Now, let's look at our forces again. The forces have suddenly become slightly more complicated. We've got 10 forwards and 5 backwards. So then we get our resultant force of 10, 5, opposite direction. The resultant force is 5. Okay? The mass remains 300, and the acceleration, again, is what we're interested in. We don't know. Now we know, having looked back at this, acceleration is force divided by mass. So we're taking 5 divided by 300. Excuse me. I just cooked with chili, so I'm basically breathing in horrible, painful air. So anyway, we can simplify our calculation a bit by dividing numerator and denominator by 5. So that gives us 1 over 60, which gives us, oh geez, what is it? I think that is 0.0166 recurring, or 0.167. And what you notice is if the force is half as big for the same mass, then the acceleration is half as big. Okay? If we double the mass, then the acceleration would halve. This time we've halved the force. Okay? Much smaller force, so we get a smaller acceleration, which hopefully makes a bit of sense. Now let's think about a little car. Okay, there's number 2. Let's go to the next moment then. So moment number 3. And what we've got at this stage is the car has got to a speed where its air resistance is equal to the thrust from the engine. So the air resistance has been increasing. There's the front, there's the rear. We've got 300 kilos. So it's sped up to a point where the air resistance is equal to the thrust force from the engine. Well, what is the resultant force here? It's 0. And be very careful, because that doesn't mean that the car has stopped. Okay? A thing to remember is, I'm going to push this little car. I'm going to try to. I'm going to push this little car. Now, I'm pushing it off screen, or you can just about see me pushing it. It's still moving forwards, even though there's no push. What's happening is that pull of friction, which is acting this way, is slowing it down. Okay? So the resultant force, as soon as it goes away from my finger, the resultant force is opposite to the way the car is moving, which means it's slowing down. Okay? So just avoid that trap of saying, this means it's not moving. It doesn't. It means it's not accelerating. Let me put in some big exclamation points to emphasize that on a line. Okay? Right? It is not accelerating. Okay? But it's still moving. The speed it's moving at is a different matter. The calculations to actually get that speed are a bit more complicated because it is accelerating. So we usually use those, we do those when we get to A level. You guys don't have to worry about it, although one of you already looked one of them up. So well done you. That sounds sarcastic, it absolutely wasn't, well done. So here we've got our resultant force. Let's just show it mathematically because we all love the maths. The resultant force is 10 minus 10 or plus negative 10, which equals 0. The mass is 300 kilos. The acceleration, well, is force divided by mass, which is 0 divided by 300, which is just 0. Okay, no acceleration. Oh, look at that. Okay, that's it for forces in motion. I'll do a separate one on weight, mass, and gravity. So there it is.